So we learned how to look at three different histograms for binomial distributions and determine which one had a p-value of 0.2, 0.5, and zero point 0.8 respectively. I want us to take a look at this graph a little bit more, where p is equal to 0.2, because I'm going to use that graph, but I'm going to modify n. So I'm going to leave n as 15, and then I'm going to change n to 30, doubling it, and then I'm going to do 70. And I want us to see what happens to these graphs when I do this. There we go. So let's look here. We have n is equal to 15, p is equal to 0.2. So this is the graph we already saw a page ago, but I've increased my scale here to 28 because I'm going to use the same scale for all problems, whereas up here I stopped at around 14 or 15 in fact. So now I'm going to kind of expand that x-axis so we can see a little bit more. Now, it doesn't really matter because, of course, it's impossible to be above 15 in this particular problem because n is 15, and that's the highest your x value can go. But now I'm going to go to 30, which means technically this graph could go to 30, which it does, and the p-value is 0.2. And you can see that the curve is becoming a little bit more, well, curve-like and a little bit less disjointed like this bar, these bars over here. Right? You get a little bit more on the left. You have kind of a left tail, and there's more of a gradual stair-stepping up and stair-stepping down from your peak. Also, your peak does not go as high as the other values. There, I just changed the scale so that they match. So you can see this goes to 0.3, and look, it's kind of gotten rounded off a little bit. So the highest high is not nearly as high as it was before here, where it's here the highest peak is at 0.25. That's not happening here. Everything's kind of getting more evenly spread amongst the bins. Now, what if n was 70? Then it becomes this curve right here. I'm going to modify that scale as well, just so you can see, because I'm going to make it so that the three scales for the three graphs match to each other. And you can see, whoops, it shrunk, and that makes sense because what's happening is that everything's getting sanded off, if you will, getting rubbed off. So what was once a super high peak at, let's see, it's about 3, had a probability of 0.25. And then what's happening is as you get n to be larger and larger, you're allowing for more and more bins to be possible or have a good chance of success. So it becomes more and more and more this curve. And that curve should look familiar to you because that's the normal curve that we were working with in chapter 3. I know it seems like a really long time ago. So as n gets larger, the graph becomes more and more bell-shaped. And statisticians noticed this many, many, many years ago in the 1800s. And they noticed that, hey, if we let n get larger and larger, then it becomes, instead of this skewed right thing, which is what this is, because there's little bitty bars right there at 8, 9, and 10, and 12. So instead of skewed right, or even skewed right here, look, there's tiny bars at 19, 18, 16. It becomes this kind of normal curve, and it's not skewed right anymore. And that's what they noticed. This last distribution where n equals 70 is very normal and bell-shaped from what we learned in section 3.2, but also all through chapter 7, 8, 9, 10. We're going to keep working with this. So that means that if n is large enough, then the binomial distribution becomes more and more normal, becomes more and more that curve, right? It's no longer skewed right or skewed left. Not that all binomials are skewed, of course. For example, this binomial distribution here is symmetric and normal curve kind of shape to begin with. But even so, it's not really normal because it's still only a few different bins. Whereas down here, we're starting to get lots of bins, right? Lots of different bars, right? Now, what is the threshold for this? What is large enough? Well, large enough is defined as, and I'll put it right here, n times p times 1 minus p is greater than or equal to 10. That's what's going to count as large enough. And sure enough, it does take place in this last problem. If I take 70 times 0.2 times 0.8, let me just type it, 70 times 0.2, right, that's n times p times, and if you like, you can do parentheses, 1 minus 0.2. I just figured out it was 0.8 in my head, and sure enough, you get 11.2. And 11.2 is bigger than 10. And that's our rule of thumb here for a binomial distribution. So binomial distribution is basically normal, approximately. Now it's not really normal because it's a discrete distribution, and a normal is a continuous distribution. But nevertheless, they're close enough as long as n times p times 1 minus p is greater than 10. And then I just wrote up real quickly what this means because it's important. We're taking discrete probability distributions. The binomial probability distribution is discrete. That's why you have bins here. These are bars here, and they're segmented. And what we're saying is, look, if n gets larger and larger and larger, then that discrete distribution becomes approximately a continuous distribution. This is what I meant long time ago in the class when I would say, hey, money is really discrete. Dollars are discrete because they end at the penny, they end at the 10th or 100th decimal place. But we treat them, quote unquote, like they're continuous. This is what I meant all along, right? This is why we take quantitative continuous discrete random variables like money and can treat them like continuous variables. This is one of the things that I meant at that time. There we go. And that treatment is very powerful for us because the normal curve and actually a couple other continuous curves we know are very potent. They have a lot of mathematical complexity and we'll be able to figure out a lot of different things from them. All right, so right there. And I just wanted to put in a little plug here for the history of this. So James Bernoulli, who lived from 1654 to 1705, was the inventor of, well, inventor is kind of a strange phrase, but he worked a great deal and was the first person to work with the binomial distribution. And Abraham de Moivre, who was alive from the 1660s to 1754, started studying that binomial distribution at length. And they both noticed that if n was large enough, and roughly n times p times 1 minus p is greater than or equal to 10, then that binomial distribution follows a very particular pattern. It wasn't until Carl Pearson came around, he's the same person that invented the correlation coefficient r from chapter 4, that it started being called normal. He coined the phrase the normal distribution. And you can see here, what I did was I took the same distribution we were working with on the last page, p is 0.2, but I let n be 500. And you can see how tiny these bars are. And look at the heights. I'm nowhere near 0.3 like I used to be. And that's okay. But what's interesting is that this whole area underneath the whole curve, all those bars must add up to 1. And you can see how close to the normal curve it is. That black curve is the normal curve. And they're very, very, very close to it. And that's what was being noticed. That function, that black curve, this is the x-axis. There's actually a function for what that normal curve is, and it's this, right? Where sigma is the standard deviation, E is Euler's number, pi is the same pi you know from circles when you were learning it in geometry, and mu is the mean. Now, we're not going to ever graph this by hand, but realize what an amazing formula this is and how it came about by studying things like coin tosses, because coin tosses are binomial, and they realized that they were forming this very special pattern, and then these mathematicians were able to figure out what the formula for that pattern must be, and we will use that formula, well, not directly, the calculator will use it to figure out all sorts of problems for us in chapter 7 and 8 and beyond. All right, we're all done with chapter 6. I'll see you back here for more on that normal curve. It's going to become your new best friend in chapter 7.